I haven't kind of.
Yes, you can.
Well.
My fruit. Nobody wants to, since we've parted ways. Okay, me neither. Okay, we can talk. Yeah.
I thought I did, and then I realized I was just doing the same thing. Just like going this.
We haven't internalized it yet.
Exactly, yeah.
Are you leaving on Wednesday?
I'm gonna leave on Wednesday.
That would-
After the formal session, we'll come back on Sunday.
Museum exhibits. Fantastic. Best no. Speaking of doing so, probably skipping like the last 2 days of next week. Museum schedules.
Yeah, you don't know when things are gonna be.
I need to know what things are where, when. Got it. Goodness.
Yeah, actually, I'm trying
Yeah, I mean, I don't know. Anyway. I love the museum one. I was trying to figure out how to say another thing without saying really funny. Yeah, maybe that makes it even better. It's basically a good job. Happens to be there.
Essentially.
Thanks. No. No.
What does sibling mean to you, son?
I don't know.
I was come up with a good,
I guess.
sisters. That you want to
It was pretty good. Very many vegetables. Oh, they have like a few. Where'd you go? Well,
Place from the. It was good. Oh, we ran through this point. Yes, they have these options. Small. Yes, randomly.
Very good. Good algorithm.
Well, I'm not really this was like an exclusion algorithm. All options include them all by
Century 27 emails.
it's exclusion. You consider each option and then.
Oh, and you like you excluded it, so you guys are just smart. Oh, I get it.
But there weren't too many.
So is this like an email exchange that you're just
I was only there. Yeah, so there's still many people.
You are gonna get them.
Yeah, I think
Likely, I mean, it's gonna be going there.
It's better.
Kevin Moore.
All right. Welcome back. Glad you opted to turn up instead of taking a nap. It's not what I would have done. Nap time. This is intense. So last time, which was like 3 hours ago, we defined circular orderability. We talked about the lexicographic construction. And from that, so if you have a short exact sequence where that side is circularly orderable and this side is left orderable, and the middle is circularly orderable. And from that, we showed that the automorphism group of any circularly ordered set is circularly orderable. And this gives us a whole bunch of examples of groups. And then Riley asked the question that if you have a circularly orderable group, is there some kind of like central extension which is left ordered? It's absolutely the right thing to ask because I drew it as a circle. You know, if you have a circle, you want to have a line somewhere. This is how you deal with circles as a topologist. You go to the universal cover. So over lunch, I rewrote the rest of my course. And, I'm kidding, that's what I was going to talk about anyway. So, but we're going to start with a diversion. And the diversion is going to be a relationship between H2 of a group, and I'll tell you what these things are, and central extensions. Right. This is something that I assume if you went to grad school in the 70s, you like learned all the time. And everyone knew it, and it was just part of, like, you go to the pub and talk about the correspondence between H2 and central extensions, but that's sort of gone out of fashion a little bit, but not that much. I'm going to go over what the correspondence, what these two things have to do with each other first, and then we'll relate it to circularly orderable groups and left orderable central extension. Okay, so let's do that. We will start with talking about this thing here. So this is a second cohomology group of a group with integer coefficients. There is a way to define this using like projective resolutions and things like this, which I'm not going to do that. Right. We're going to do it very concrete. We're going to get as concrete as you can. And I'm going to, like any good cohomology theory, there's a Z and a B. And I'm going to define this. So this is the cocycles. So these are the set of all functions from G squared to Z. Right now, for this diversion, we have nothing to do with circular orderability or left orderability. Right? This is just back in group theory land. All right, so it's functions from G squared to Z such that, and they satisfy some condition. Right? And what's the condition is that f of, all right, G2, G3 minus f of G1, G2, G3 plus f of G1, G2, G3 minus f of G1, G2 is equal to 0. For all G1, G2, G3. So this is, and f of the identity and G is equal to f of G and the identity, which is equal to 0. Okay, so this has a structure of an abelian group because it's functions to Z, and Z has a structure of an abelian group. So you can add functions together. Okay. How do you remember this? You think of this as 3 things, and it's like a Newton's cradle, like those pendulum things. G1 comes from the outside, and then it knocks into G2 and knocks G2 across, and then G2 knocks G3 out of there. Right? That's how you remember it. Straight through.
Is it like a homomorphism or is it just a map?
It's just a function. It's just a function, a set map. Great. So these are the 2 cocycles. Here are the boundaries. Is going to be equal to the set of all functions from G squared to Z, satisfying there exists another function H from G to Z such that H of the identity is equal to 0 and f of G1, G2 is equal to H of G1 plus H of G2 minus H of G1. So this condition here is saying, you know, H is just a set map. It's not a homomorphism. But let's look at all the functions which measure H's how much H isn't a homomorphism. What's the defect of H being a homomorphism? If this was 0, that would imply that H is a homomorphism. Great. Right, they're just 2 abelian groups, and you can define H upper 2 G with integer coefficients to be Z. The co-cycles over the co-boundaries. Okay,
So if I had a, sorry,
go for it.
if I had a G module A,
Yep.
would I just play the same game?
Yes. So more generally, you could replace Z with an abelian group. Or more generally, even, you could replace Z with a module on which G acts. And then you have to change the definition of co-cycle a little bit. But what's actually going on here is G1 is acting on this. There's some actions that you have to pay attention to, but here it's a trivial action on Z. And that's all we're going to care about. Yeah.
As a dirty topologist, my definition of group homology is you just look at the homology of the KG1.
Yeah.
It's
They're the same.
Yes, I know, but is it going to be clear that they're the same?
No, I don't think so.
Okay.
So there's a different way to define the co-cycles where it's more clear that it's sort of an alternating sum of faces of simplexes. It looks more like an alternating sum of faces of simplexes, but other than that, no. Not to be.
I think how it works is there is a construction of KG, and when you take some not singular cohomology but cellular cohomology, then you'll get this formula, something like that.
Yeah, I'm ignorant, but Max might be less ignorant.
You add some one edge for each element in a disk for every relation, and then you do something, you're saying you might get something that looks like this.
Yes, exactly. This is, I think, how it works, if I remember correct.
This is an abelian group. This is a subgroup. You can check. It's not clear from the definition, but it is. It's a subgroup. So this is an abelian group. An abelian group. Okay. Very little intuition to be had just by looking at the definition. But let's talk about the other side of the story now, central extensions. And then we're going to show how elements of H2 actually parameterize these objects. Okay, so let's talk about central extensions. So definition. So a central extension, a Z central extension of G is a short exact sequence 1 to Z to G tilde, let's say, to G to 1. Let's make that map iota such that iota of Z is central in G tilde. And that's what a central extension is. 2 extensions are going to be equivalent. So in order to set up this correspondence between H2 and central extensions, we have to talk about equivalence classes of central extensions, really. So 2 central extensions are going to be equivalent. So say you have, so you've got your Z here, then you've got a G1 tilde, 2 tilde, Z. So the top is a central extension. The one on the end. Yeah, thank you. Good. I should have napped. The top is a central extension, the bottom is a central extension of G. When are these equivalent? It's exactly when there exists a homomorphism, right? So these two central extensions are equivalent if there exists a phi. So let's do it over here. There exists phi from G1 to G2, so that both these triangles commute. Okay, so if I start here and go there and then down, that's the same as going here. I'll start here and go across, that's the same as going down and then across. So that both triangles. Exercise is that if you have a group homomorphism that does this, it's an isomorphism. It's a group theory exercise that you can. So such a phi.
Oh, it's the 5 lemma.
Is it? Yeah, I guess it's a 5 lemma, but like you could just it is a 5 lemma with a bunch of identities, I guess. Yeah. On a billion. So that triangles. So such a phi is necessarily an isomorphism. But it's stronger than an isomorphism, right? It's an isomorphism that restricts to the identity on the Z subgroup and gives you the same induced map. Well, restricts to the identity on G. Well, sorry, quotients down to the identity on G. This is a very strong kind of isomorphism. So for example, here are two central extensions of Z mod 3. Those two central extensions are not equivalent. They're different because the groups in the middle are not isomorphic. Okay. Cool. Questions about these definitions? So the goal before we get back to orderability is to talk about how you can start with an element of H2 and build a central extension of G, and start with a central extension of G and build an element of H2. And then it will turn out to be that that's a bijection between those two sets with some nice properties. So let me write this down. Are not equivalent. These are not equivalent. Let's just have some notation. Let curly C E. Oh, that's too many curls. It's just out of control. There we go. Be the set of equivalence classes. Of equivalence classes of Z central extensions. Here's a theorem. It's, I guess, a classical correspondence. There is a one-to-one correspondence between C E of G and H2 the coefficients in Z. And even better, whatever this correspondence is, such that there's a special extension here, which always exists regardless of G. And this one to Z cross G to G, 1. And it's such that this one corresponds to 0. So not only is there a one-to-one correspondence, but if you're interested in the trivial element in H2, that maps to the split short exact sequence. The one where this is just a direct product of these two things. All right, so let's talk about how this works. Other questions about what the theorem says?
The correspondence of sets.
It's a correspondence of sets, but you know, the thing on the right is an abelian group. I don't really know what it means to add two equivalence classes of short exact sequences, besides moving over there and then adding them back. Maybe there's a neat way to think about these, but I'm unaware of it. Okay, so when I say proof here, I mean I'm going to tell you how the correspondence goes and then not check any of the details. So it's a lot of bookkeeping, but that's not the important part here. Okay, so let's take an element in H2. So remember, an element in H2 is an equivalence class of a 2 cocycle, right? So it's a function which satisfies that pendulum condition. All right, so now we're going to define a group G tilde subscript F. To remind me, it's coming from F. As the group with underlying set, Z cross G, but with multiplication defined a little strangely. Equation defined by because I take N and A and M and B, and I multiply them together. So integer group element. I'm going to multiply them together almost like I usually would. N plus M, and then over here I'm going to have A times B, but this coordinate gets twisted a little bit. Something strange happens to it. And I add plus F of AB. The hard thing to check is associativity, but associativity comes from the fact that F is a 2 cocycle. It satisfies that strange condition. This is a group, and notice or check if we want, all right, that we have 1 goes to Z, goes to G, tilde F, goes to G, goes to 1. Let's call this iota and phi, and let's see what the maps are. Iota of N is just N comma the identity. And phi of NG, or let's call it A to be consistent, and A is equal to A. Okay. So you can build a central extension just from that F. We've left tons of details under the rug, checking everything's a homomorphism, checking that G tilde is a group at all. And also checking that if I have 2 Fs that represent the same class in H2, that they give you equivalent short exact sequences. But it's true. Again, fun exercise for some definition. That's one direction. So this starts with an element of H2 and gives me an equivalence class of short exact sequences. Now I want to start with a short exact sequence and come up with an element of H2. Are there questions about how this works first, though?
Example you have in mind when you think of this?
That's an example I have in mind. Like there's a you can take G to be S1. This is the example I have in mind. G to be F1, and then the 2 cocycle somehow comes from the circular ordering on S1. Right? There's like a way to build the 2 cocycle, which we'll come to in a moment. And then this group turns out to be the real line. So it really is like your unwrapped, or F is 0 math. And then this group is just G cross Z, Z cross G. There's nothing interesting with this multiplication now. So conversely, start with 1 to G, sorry, Z to G tilde to G. 1, let's call this. All right, what we're going to do is we're going to pick. I'm going to draw it like this, and what we're doing is we're picking coset representatives of Z. Okay, so choose a function S from G to G tilde such that S of the identity is equal to the identity. And if I start there and go there and then back, I just return to the identity. So P of S of V equals G, all G and G. And this is another way of just saying pick coset representatives of Z inside G tilde. And make sure that the coset representative of Z is just the identity. This is just a function, okay? If there's a homomorphism you can choose, that would imply that this group in the middle is isomorphic to Z cross G. But that's not always going to be the case. So if there was a homomorphism you can choose, great. You're not always going to be able to do that. Okay, now we're going to define.
Sorry,
Yes.
if you had a homomorphism, like the Klein-Bottle group, there it's Z by Z, Z, but it's not Z cross Z.
Yeah, because it's not a central extension.
Okay, thank you.
It's a non-trivial. Good. Remember, I'm insisting that this is central extension. Good question.
I mean, even if the thing in the middle is isomorphic to the product, it doesn't necessarily mean you're coming from the identity element, right?
It doesn't mean that.
You're coming from the identity element, right? Because in the example, we break down, we said, well, we can break down 2 sequences But there should be 3 extensions. So the third one is coming from a non-trivial.
Yes, that's exactly right. Yeah, that's right. So there could be an isomorphism to the direct product where it doesn't correspond to the identity cohomology class. Is that what you're saying?
Yeah, because I think, there's some missing information in that sequence you wrote, and on the theorem, you didn't specify what the maps were.
Oh, right. This is literally projection. Yeah. Okay.
Right, the inclusion onto the third.
Right. This is pi2, and this is inclusion 1. You're right. The actual maps do make a difference with the equivalence class of essential extension. Thanks. Okay, so now what are we doing, right? We're starting with essential extension, and I want to end up with a cohomology class. So I need a 2 cocycle. So this is what I'm going to define now. So FAB is going to be, well, we're going to call it iota. Here's my iota. Iota of FAB is SA, SB, SAB inverse. I have to check that everything makes sense. I didn't write down some nonsense. I'm going to check that I didn't write down some nonsense. Okay, so why is this all right? Because if I apply phi to the right-hand side, phi of S is the identity. So what I would just have is I would have A times B times A times B inverse, AB inverse. So that would be 0, which means so phi of this is 0, which exactly means that this has to live in the inclusion of Z. Means I can write this down, right? Because I want this to be an element of Z, not an element of G tilde. That's why I've written iota of that. Now we have F in H2. Again, you have to check a whole bunch of things. You have to check this is a cocycle. Well, you have to check it's a cocycle. Then it gives you an element, and then you have to check this whole thing is a bijection. Okay, but this is how you move from one side, right? This is how what I just showed you is how you move from here to here.
That cocycle looks a whole lot like a formula for a coboundary if you replace multiplication by addition.
Yeah, it does. You're right.
But S doesn't hit Z.
No, yeah, exactly. S doesn't land inside Z, right? Z.
Right.
Yeah, but I mean, it's a good observation, because what you're saying is you want F to measure how much S is failing to be a homomorphism. That's what F is measuring. How far away from homomorphism is S? If S is a homomorphism, it's very close to homomorphism. In fact, F is 0. So it would give you the 0 cohomology class. Okay, so I'm not going to fill in the details of this correspondence, but we need to know how it works in order to move on. This gives the one-to-one correspondence. QED, yeah.
Sorry, could you say again what I don't understand how this is landing in Z.
Oh, right. So we want F to be an F of AB has to be an element of Z. So in order for this to make sense, saying, okay, what I want this element here is an element of G tilde. Right. So I'm including my element of Z, which I want F to be, into G tilde, so that I can write down this equality sign because it lives in G tilde. This equality lives in G tilde. I see. Yeah, but you show that really the right-hand side actually lives in the image of Z.
Oh, okay, right, cool.
Yeah. Or the alternatives, you can be like a little bit, you can abuse notation a little and just say that. Right. And know that this is living inside the inclusion of Z into there. Okay. So where are we going with this? So we have this one-to-one correspondence. What we want to do is we want to exploit this correspondence and say, I start with a circularly orderable group. And a circular ordering on a circularly orderable group is actually an element of H2. So it gives you a central extension, and we're going to endow that central extension with a left ordering. So we're going to have this sort of way of passing from a circularly orderable group to some universal cover. It's kind of like S1 unwrapping in time. That's a picture I like to have in mind anyway when we're doing it. So let's try to do that now. Okay, so in order to get there, first I need to associate a circular ordering with a 2 co-cycle. And those are the key. I might have said, wait, you already gave me one, but I'm going to give you a better one. C, circularly ordered group. So C satisfies one of the conditions on C, the thing that made it a circular ordering, actually tells you that C is a 2 co-cycle, but it turns out to not be the one that we want. So we're going to adjust it a little bit. Yeah, it's not great. And okay, let me write down the definition and then we'll try to justify that this is an okay definition. So we're going to define F coming from C. I'm going to write it like that. From G squared to Z as follows. FC of G 0 if G equals the identity or H equals the identity. 1 if GH equals the identity and G does not equal the identity. And a half 1 minus C identity G GH otherwise. Okay, this should mean nothing to you, but we have to draw pictures to justify what's going on.
This is maybe like rechoosing it within its cohomology class, so it's better or something.
It's actually giving you a different cohomology class. Yeah, that's equal to minus a half of the original cohomology class, something like this.
Yeah, that's weird.
Yeah, it is weird. Where this is actually coming from is that you look at an action on subsequent, like R or some on S1, and then you're taking the Euler class of this action, if this means anything to you. Right? Or you can do this algebraically. So here's what's going on.
Sorry, did you say already why the original one doesn't really work?
No, I didn't say that. I didn't say why. It's not the right one, because I'm going to prove that this one gives you a lot of nice results. Okay, I mean, why is it not the right one? At least from what I just said in the first half of the lecture, right? I want to construct a central extension, right? And how do I construct it? I need a map from G squared to Z. And C is a map from G cubed to Z. So I want to adjust it a little bit. Maybe that's not satisfying. Let's have a look at what's going on. So I want to draw a picture of what happens. So this is identity G and GH. This is exactly saying that FC of GH is equal to 0. And here, let's draw another one, identity G GH. This is saying that FC of GH is equal to 1. Okay, so here's the way I like to think about this 2 co-cycle. I want to know what FCGH does. So I start with G, I start with the identity and I go, what's happening with G? And then I multiply it by H and I check, does H force my G to wrap all the way around past the identity or not? So if I multiply by H and I don't get all the way around the identity, then I map that to 0. If I do get all the way around the identity, I map that to 1. So really this number is just counting. When you take G and then multiply it by H, how many times do you pass the identity? If you think of we're always moving in a counterclockwise direction. And this formula turns out to exactly capture that. It's just a neat way to write it down. The advantage of doing it this way, oh, sorry, there's a couple of interesting things about this, right? This only takes in 2 arguments, but a circular ordering on a set takes in 3 arguments. You might be like, we're losing information, we've got to be. This only works when you have a group. You have a circularly ordered group. So somehow the group multiplication, the group structure is being taken into account here now. When you're passing here. In fact, let's put here, fact, that FC is a two cocycle. So it defines a cohomology class here.
I don't really understand what it would have meant to take the original class defined by C, since it's not even.
Yeah.
Yeah.
So you can define group cohomology in a couple of ways. And one way is you can take what are called homogeneous cocycles. And C is an example of what's called a homogeneous cocycle. So yeah, if you haven't seen that before, don't, it's not terribly important.
What if FC of GH is the identity?
If FC of G, you mean if G times H is the identity?
Yes, what if?
Yes, okay. Yeah, if G
H
times
G
H is the
inverse.
identity, then I'm gonna make that equal to 1. That's what this line here is. If G times H is the identity, so if you go around and you just touch the 1, touch the identity, you make that 1. You're still passing the identity.
Okay,
Thanks. So I have some 2 cocycle, but before we talk about the central extension, I want to maybe give you a hint that we can actually rephrase the whole definition of circular orderability in terms of 2 cocycles like this. So now suppose that f from G squared to Z is a 2 cocycle satisfying, where are we? All right, such that satisfies 2 things. F of GH is in 0 and 1, and F of G inverse is equal to 1 when G is not the identity. You can define a circular ordering from a cocycle like this. You can go back the other direction as well. And define C coming from F of G1, G2, G3 be equal to 0 if Gi equals Gj for some I not equal to J. 1 minus 2 F G1 inverse G2, 2 inverse G3. So the point of this is not so much what the actual formula is, but you can start with a 2 cocycle that takes values in 0 and 1 and has this property. And it gives you a circular ordering. Okay. So this is CF is a circular ordering. CF is a circular ordering on G.
That definition, why? It's G2 inverse G3, not G1 and.
Yeah, it's G2 inverse G3. It's what exactly undoes the first process. Yeah. I mean, you can look at this picture as to what the F's doing and recover the C from that. You can try to rewrite down this formula for this. All right, here's a fun fact. Is that theorem is that F mapping to FC and C mapping to C subscript F. So you start with a 2 cocycle, map it to a sorry, I've done this the wrong way around. Start with a 2 cocycle, map it to the corresponding circular ordering. Start with a circular ordering, map it to the corresponding 2 cycle. This is a bijection between the set of circular orderings and 2 cocycles satisfying this. It's a bijection between circ orderings on G and 2 cocycles that F of GH is in 0, 1 and F of G inverse is equal to 1 or G not equal to the identity. Okay, so the take home from what just happened is that I can have an equivalent definition of a circular ordering, which is a 2 cocycle that takes values in 0 and 1 and takes 1 on GG inverse and GG inverse. And that's an equivalent definition of a circular ordering. And I like this because now I have a 2 cocycle, so I can play this game of getting central extensions from. You know what's going to happen? Yep.
Can you look at the central extension until if it comes from a two co-cycle of this form? Does it have a special form or?
You can. I think it'll become clear as we go along. Sure, I mean, I'll just tell you the answer. It's if the central extension is left ordered with what's called a cofinal central element, some property about the left ordering, then it has to have come from the co-cycle on the quotient group with this property.
Okay, thank you.
Who proved this theorem? Who proved this theorem? It's from 70s. I think it's Aleva. Is this a?
I think that in pieces groups acting on the circle is where you find that these all like co-cycles have these properties correspond to circular orders, but it might have been known before then. I'm looking at Andres because he might know where it came from first.
Yeah, it's a paper that he published in the Journal of the Mexican Mathematical Society in the 80s.
Okay. Yeah. Yeah. So this, I mean, sort of one way to look at this and where it comes from is you look at actions on the circle. And this is exactly the Euler class, whatever that means, of the action on a circle. It's sort of how much wrapping around a circle happens. Okay. So here's what's going to happen. We have our circle. We have a circularly orderable group, circularly ordered group G. And I'm going to think of this as a two co-cycle FC, right? It's just the circular ordering is F. It's a two co-cycle. So it corresponds to some G tilde F. And there's a Z here, one. And what does this group look like? Well, it's a Z central extension of G. Here's the identity. Here's one, here's two. Actually, I'm going to call this Z. Here's Z squared. Z inverse. And here, iota, and iota of 1 is equal to Z. So inside this group here, you've got some central element, right? This is a central extension. And when you start with a circular ordering, you can draw this picture for the left order, for the central extension, where you sort of take this, cut it along the identity, and glue countably many copies next to each other to create something that looks like R. And when you have something that looks like R, it's a left-ordered group. You put the group on a line. So this is what's going to happen. We're going to construct a left ordering on this, coming from the circular ordering. Let's see. And it's going to have some properties about some central element going off as far as you want it to. So let's do that. First, a preliminary definition. So G, this, so you have a left-ordered group. An element Z in G is what's called cofinal. If it behaves like this, right, powers of it end up filling up the whole group. More precisely, if for all G in your group, there exists an N in the natural numbers such that G gets trapped between Z to the negative N. Equal to G less than or equal to Z to the N. Actually, I don't need the equals, just less than is fine. So every element eventually gets trapped between two powers of Z. That's what it means to be cofinal. Sort of fills out your whole group.
Why can't you take two consecutive powers?
I can. Don't want to. You can show that if there's a central cofinal element, so the picture lies like this, and every other element does lie between two unique consecutive powers. That's true. Okay, so let's construct this left ordering on the lift, on the central extension. And you think of this as a universal cover of S1. At least that's how I like to think about it. So, given a circularly orderable group, GF, and now when I write F, I mean it's a two co-cycle.
Yeah.
Okay, I'm going.
Consider G tilde F, right? Which is, I'll just remind you of the construction, right? As a set, it's that but with the multiplication, it's MB equals M plus M plus FAB. And so this is exactly the central extension corresponding to the cohomology class. Define a positive cone in A and G, so that F that N is greater than or equal to 0 without the identity. Right, but these are the positive ones. And sorry, going back to this picture, this is exactly saying, so what turns out to be the corresponding picture is that this little interval here is all the things that look like 0, comma A. This interval here is all the things that look like 1, comma A. This interval here is all the things that look like 2, comma A, etc., and that's the positive cone. And you can show as an exercise is that 1, 0 in G tilde is cofinal and central. We already know it's central because we're talking about central extensions, but you can show that it's cofinal with that ordering. So we lifted. We started with a circularly orderable group. We went to a central extension. Now we're going to start with a left-ordered group with a cofinal central element and quotient down to a circularly ordered group. So it's lifting. Let's project now. So let's suppose you start with a left-ordered group, and Z in G is positive, cofinal, and central. Cofinal and central.
There's a big chunk here. If you
Oh, thanks. Gone wrong for now. Okay, so what does this mean? We have, you can look at the subgroup generated by Z. It's central, so it's normal, so you can quotient by it. Iota of 1 equals Z. We're going to circularly order this. Where we want to take the left-ordered central extension, or the left-ordered group with a cofinal central element, and circularly order this. How are we going to do it? We're going to pick a section and then take the corresponding 2 cocycle. We choose S so that S of GZ is the unique coset representative of the coset GZ, such that, so I'm going to write it bar of G bar of GZ, so that the identity is less than or equal to G bar is less than Z. Okay. Let's go back to this picture. So your section is, you're just choosing the elements which lie in here, in between the identity and Z. And that's a full set of coset representatives. So that's what you're choosing. And then the corresponding 2 cocycle you can check is the circular ordering. What's happened, right? We've got this correspondence now between circularly orderable groups and left-orderable groups with cofinal central elements. You can move back and forth between them by quotienting and by lifting. Here are some examples of what this looks like. Examples, G is equal to S1 with the standard circular ordering. G tilde is equal to R. And your cofinal central element is the element 1. This sort of lends itself to the idea that this is some kind of universal cover of your circle. If G is equal to Z mod NZ, G tilde is equal to Z, and your cofinal central element in this case is N. If G is equal to Omeo plus
Z mod NZ with the
standard circular ordering, where equivalence class of 1 is the smallest generator in the circle. Omeo plus S1. There's a circular ordering on this where G tilde is homeo plus S1 tilde, which notationally doesn't tell you very much. It's all the homeomorphisms of R that commute with translation by 1. That's what this group is. And Z is X maps to X plus 1. There are some other curious examples that you get. So you can take G being SL2Z. There is a circular ordering on this, where G tilde ends up being the braid group on 3 strands. And Z is the full twist. And Z is that braid group element. Lots of really nice sort of correspondences you get here.
People bring some kind of side normal form or something.
Yeah, yes. There's something called you can use a Gauss-side normal form in B3 to define a left ordering in the braid group. And this is a central element, it turns out to be cofinal in that ordering. That's exactly right. Okay, so I'm gonna stop there, and then when we come back, we'll just fire off a whole bunch of consequences of being able to go back and forth between this. We did the hard work. It's disappointing. Anyway, see if we can get some consequences.
Question. So on this board here, you have this P that you define. That's supposed to be a positive number. Are there some restrictions on little a?
No,
because it seems
as long as it's not, as long as this element's not the identity.
Oh, okay. So as long as okay,
Remove the identity.
That is 0. Then
Yes. Sorry, but if n is 1, then a can be anything, and if n is 0, a just can't be the identity. So it really should be this without the identity.
But then if n is 0, then a and like 0 comma a and 0 comma a inverse, or what would it? So what would
0 comma a inverse is not the inverse of 0 comma a because the group multiplication is odd.
I mean, I understand that, but
yeah. So 0 comma a inverse. Sorry, 0 comma a inverse is actually equal to -1 a inverse in this group.
Oh, right.
It turns out.
When you're dealing with a topological group, is there some way to make this construction respect? Because
yeah, they are suggested, right?
Yeah.
That is not something I thought about. I mean, I guess you'd have to have the topology on your group. If the topology on your group was the order topology on the left ordering or the circular ordering, then probably sure comes up right.
But sorry, wait, if this construction goes through group cohomology, if we just take the usual group cohomology of a topological group, this does not respect the topology of the group in the first place. And so one way to get around that is to take continuous group cohomology, where you impose that all the co-cycles and co-chains are continuous, but then you might not get this construction in the end. So it doesn't seem obvious to me how you would get around these issues.
I don't know.
Tyrone, could you say a little bit more on why SL2Z is circularly orderable?
Oh, now you. So here's why I know it's circularly orderable. Okay.
It acts on the hyperbolic plane.
it's on the circle.
Yeah. So here's one way you can maybe see it is so take SL2Z as acting on R2 in the usual way. You take the unit circle, and then that does something to the unit circle, but then you can normalize. And because you're a determinant 1 matrix, you're going to preserve the order around a circle. It's sort of a not very satisfying answer, maybe, but it acts on the circle. But also acts on the hyperbolic plane. Sorry?
Action on the boundary of hyperbolic plane has a kernel.
It has a kernel of ±1.
Also, it's the quotient of B3.
It's quotient of B3. This is what I like best. It fits. I mean, this is why I know it's circularly orderable. Right? It fits into this one exact sequence.
I thought that's PSL2Z. Yeah,
Oh, that's what you're missing. Yeah, you're missing.
it's PSL2Z. That's the quotient. But generated, it's like generated by A and B, and A squared equals B cubed equals the identity.
But if I quotient out by the half twist, sorry, not the square root of this full twist. What I'm thinking of is a mapping class group of once punctured torus. Right? That fits into a short exact sequence where you've got a mapping class group of a torus with one boundary component, and then you cap. The one boundary component is B3. When you cap, you get SL2Z. But I think the difference of what's going on there is that there's some. So this element in the braid group, which is usually called delta, it's like a full twist, but it's really a square of a full twist. Right? So if you mod out by the square of the full twist, you get PSL2Z. If you mod out by just the full twist, you get SL2Z. I think this is what's going on.
But the square root itself is non-central. Aggregates the two.
So okay, the element I want to quotient out by on the disk with 3 punctures is the Dane twist around the boundary.
Oh, that sure is the full twist.
Full twist.
You quotient by the square, you get something larger. You actually want to quotient by the square.
Yeah, you want to quotient by the square. No, you're right.
Yeah, so you just need a P.
You get P. Yeah.
Sorry. So I want to quotient by T alpha squared, the Dane twist around alpha squared, which you get SL2Z there. And the reason where is this coming from in my head? Let's just go for it.
Oh, good. Thank you. Good.
Yeah, you like this better? So the mapping class group of a torus with one boundary component is B3. Sorry for those who.
Sorry, is SL2Z.
No, with one boundary component, it's B3.
Oh.
So we have to fix the boundary component, and then there's a map from here into the mapping class group with one puncture by just capping on, and this is SL. And this element is cofinal and central in a left ordering on B3. This is why I know it's circularly orderable, Dale. Sorry.
Thank you.
Yeah. But I don't know of a nicer way to see this. I mean, there are experts in the audience who know much more about this than me. Like, what's the standard way to see that SL2Z is?
You know, you were saying, you take the action on the outlines.
Sorry?
You take the action on the outlines of on the plane, in the plane. That's a circle.
Oh, right. Okay. Yeah. Great. On the lines passing through the origin. Yeah. Okay. Okay. That's a circle. Yeah. And because the determinant's 1, it preserves the circular ordering. Good.
See why you want the square from.
Okay. Any more grilling?
I can't resist. Are these processes inverse to each other?
Yeah, they are. Exercise. This gives you an equivalence of categories between some category of circularly orderable group and some subcategory of left orderable groups, where you have to insist that your morphisms are injections, but other than that, it's actually an inverse process. So really, if you want to deal with circularly orderable groups, your first port of call is sort of left orderable groups with cofinal central elements.